I welcome all the students. Today we are going to start with the unit number 5. The name of unit is three-dimensional geometric transformation, and then we are going to learn curves and fractal generation. Okay, so the point that we are going to learn today is about 3D transformation, and the sub point of 3D transformation we are going to learn the 3D translation in detail. Okay, so our today's topic of discussion is 3D translation, okay, which comes under the basic 3D transformation. Okay, and after that, as per our syllabus, we are having the next point: 3D rotation, 3D scaling, 3D reflection, composite transformation, projection, types of curves, and so on. Okay, so this emphasizes the complete unit, that is unit number 5. Okay, out of that, today we are going to learn the topic 3D translation. Okay, let us move to the discussion. Basically, first we are trying to learn what is meant by the 3D transformation. Okay, we have already covered the 2D transformation in detail in previous session or previous unit. Let us understand how I can move from 2D transformation to the 3D transformation. Okay, so the first point is the methods for geometric transformation and object modeling in 3 dimension, okay, are extended from 2 dimension. So as we are already knowing about 2 dimension, which is having the x and y coordinates, so we are going to extend this 2 dimension into the 3 dimension, okay, or 3 dimensional transformation methods by including the coordination, okay, by including the coordination for, or we can include the z coordinate value. Okay, so in addition to the x and y coordinate which are used in the 2 dimensional form, we are going to use the one more coordinate, that is the z coordinate, okay, will be included or added to convert this 2 dimensional transformation into a 3 dimensional transformation, okay, or 3D transformation. Now we translate an object, okay, by specifying the 3 dimensional vector which determines how much the object is to be removed, or it is moved, how much the object is to be moved in each of the 3 coordinate direction, in x direction, in y direction, and obviously in the z direction. Okay, so now we translate the object. Okay, whatever the object, we perform the transformation of the 3D object. We have to specify the 3 dimensional vector, and that determines the how much the object is to be moved. It may be translation, it is moved. If it is rotation, it may be rotated, it may be scaled. Okay, in each of the 3 coordinate direction, that is, we have to consider its movement of the object in x direction, y direction, as well as the z direction. Okay, so this is what the basic we are having related to 3D transformation. Okay, now as in the 2 dimensional transformation, okay, we express the as we have used in the 2 dimensional transformation, we also express the 3 dimensional transformation in the matrix form. Okay, so we have to represent all the type of 3D transformation. We are going to represent all this 3D transformation in a matrix form also, as we have represented in the 2 dimensional transformation. So our aim is not only to consider the 3D transformation, okay, but we have to also consider the matrix transformation matrix, how the transformation matrix is represented, how the transformation matrix is used, okay, in the 3D transformation also, as we have defined the 2D transformation for all 2D translation, 2D scaling, 2D rotation, reflection, shearing, and so on. Similarly, we have to consider all this transformation with the matrix form or matrix representation of the same for the 3D transformation. Okay, so now we are just moving to the slide, okay, next slide, to understand the further details. Our first thing that we have to learn, we have to concentrate on how a point in 3 dimensional space is represented. Okay, So the 3D transformation, my point is represented as it is having the value x, y, and z. So it is having the direction x direction, y direction, and z direction. Okay, is represented by a 4-dimensional position vector. Okay, all of you know why it is required for one more dimension, considering the homogeneous coordinate system. Okay, considering homogeneous coordinate system, the point x comma y comma z is represented in a 4-dimensional position vector as, okay, how it is represented you can find, it is represented as x comma y z and 1. It is 1 indicate that we have used, it is for the h, this factor is called as h, it is used for the homogeneous coordinate system. Okay, so my point in the 3D, my original point in 3D is x y z, was now represented as x y z and 1. Okay, so this is my original object. Okay, now suppose my original object, okay, I want to multiply it with the transformation matrix. So this is my 3D transformation matrix. Okay, so this is my point multiplied 2, I take the matrix multiplication of it with the transformation matrix. Okay, my transformation matrix here, it may be translation matrix, 3D translation matrix, it may be 3D rotation matrix, it may be 3D scaling matrix, and so on. Okay, and after multiplication, whatever the result I am getting, okay, this is my transform object. Okay, and it is having the value x dash, y dash, z dash, and h. Okay, maximum time we are considering this h value is always considered to be 1, but we get the we can say calculated value or the new value for the x dash, y dash, and z dash. Okay, so this is what that we are considering. Okay, or in another case or another representation, or in different textbook, this may be represented as, suppose this is my x. Okay, so this is transform, so I get it as x dash or x star. Okay, I consider this is my x star. Okay, so this x represent the, it may be the point, it may be the line, it may be the object. So I can say x star is equal to, this is nothing but it is my original object, maybe a single point, getting me, or maybe a line, maybe a polygon, maybe any object. Okay, this is x is my original object multiplied by this transformation matrix. So x into t, I get x star or x dash, okay, which is my transformed object matrix. Okay, so let us continue our discussion here. See, where the, just now we have seen what is the t indicate, the t indicate the transformation matrix. Okay, so to indicate the transformation matrix that I'm using, for translation I will use translation matrix, for rotation I will use rotation, for scaling I will use the scaling matrix, and so on. Okay, so the transformation from homogeneous coordinate to ordinary coordinate is given by, see here we have added this one. Okay, we have added this one which indicate the h value, and that is what we have represented here as h value, which is equal to 1. Okay, so how this will be, the normal xyz or this value is transformed from the homogeneous coordinate to the ordinary or normal coordinate system, is considered generally as, what is my x star value is equal to, so my x star value is x dash upon h. Okay, obviously I'm having the value of h is equal to 1, so I will get this is equal to 1. Okay, so I get x star is equal to h dash upon h, y star is equal to, or y dash is equal to y dash upon h, z star is equal to z dash upon h, and this value is always 1. Okay, so everyone knows that x star is equal to x dash divided by, we have to divide this x dash, y dash, z dash by the h value. That's why I told generally the value is 1. So any number divided by 1, I get the same number as it is. Okay, so this is what our representation of the 3D point with respect to the homogeneous coordinate system. Okay, now here in 3D transformation, by considering the homogeneous coordinate system, we are going to use a general 4 by 4 transformation matrix. So in 3D, my transformation matrix, or what is my size of transformation matrix for 3D, is 4 by 4. Okay, so my transformation matrix is 4 by 4. Okay, and how it is represented, let us understand this. See here, it is represented, my t is represented as, t is my transformation matrix which is 4 by 4. Okay, and how it is represented, generally we represent it into the 3 by 3 form. Okay, I just divide this matrix into the submatrix for the simple understanding purpose. Okay, you come to know that how these numberings are given. So I'm having this first 3 by 3. So it is having number A, B, C, D, E, F, G, then H. Why I'm not using H here? Because H is used as a homogeneous coordinate system. H is represent, small h represent homogeneous coordinate system. So H is not used. So I'm having A, B, C, D, E, F, G. After G, I'm having I and J. Okay. Now similarly, I'm having represent this as L, M, and N. Generally, it is used for the translation purpose. Similarly, I'm having this represented as P, Q, R, and this is used as a S. Okay, so I'm having PQRS. This is my LMN. Okay, so this is the way my transformation matrix, my 4 by 4 transformation matrix is represented. Okay, so in the next slide, we understand why I have divided this into 3 by 3. This is separate matrix. I think I divided it into 4 parts. This is separate. This is separate. This one is separate. This complete S is separate. Okay, so what was the purpose of dividing it and why we are giving the numbers separately? Okay, so let us understand this, okay, in the next slide, and how this 4 by 4 transformation matrix represent. See, the 4 by 4 transformation matrix can be partitioned into 4 separate sections or submatrix. I think just now I have shown, I have divided it into the 4 separate sections or 4 separate submatrix. Okay, how it is divided, you can find out. This is my 1. I think just now I have shown it here in the previous slide. So this is my 3 by 3 transformation matrix. Here I will get it is 1 by 3. This is my 3 by 1 and this is my 1 by 1. Okay, now what is the spatial understanding of this? Okay, what the type of transformation this submatrix represent? Okay, now to understand this, okay, I just continue with our discussion here. First point is the upper 3 by 3 submatrix. Okay, which is upper 3 by 3 submatrix? This is my upper 3 by 3 submatrix. Upper 3 by 3 submatrix produces a linear transformation in the form of scaling, shearing, reflection, and rotation. Means all linear scaling, shearing, reflection, rotation will be performed by this 3 by 3 submatrix. Getting me? So that's why I'm having the what type of transformation, 3D transformation are represented by this 3 by 3. So it is linear scaling, shearing, reflection, and 3D rotation. All these are performed with the help of this 3 by 3 transformation matrix. Okay, so let us understand next submatrix, the 1 by 3 lower left submatrix. 1 by 3 lower and left side. So which one it is? It is this matrix. So and say 1 by 3 lower left submatrix produces the translation. See here, the translation is not produced by 3 by 3 submatrix. Here I'm having in step number 1 or first 3 by 3 submatrix, I'm having scaling, shearing, reflection, and rotation, but I don't have translation. So which is going to perform or produces the translation is my this lower 1 by 3 lower left submatrix produces the 3D translation. Getting me? So let us move to the next point. This is considered as the upper right. Okay, so upper right 3 by 1 submatrix. This is my, just understand, this is my upper right side 3 by 1 submatrix. Getting me? 3 by 1 submatrix. What is going to produce? It produces the perspective transformation. Okay, so we are learning this perspective transformation also as a separate section or separate lecture. So upper right 3 by 1, this I think we have represented as PQR. Okay, so this is PQR represent produces a perspective transformation. It is used to produce perspective transformation. And now what is remaining? I think this is over, this is over, this is also considered. So remaining is only this 1 by 1. Okay, let us understand what this performs. So you considered here, okay, the number is I consider it as 4. Okay, this is the fourth point that we are having, the lower right 1 by 1 submatrix. Okay, so this is my lower 1 by 1 submatrix. This one, lower 1 by 1 submatrix produces overall scaling. Okay, so this is the special purpose 1 by 1 submatrix which is going to produce the overall scaling. What is mean by local scaling? Local scaling means it is in the scaling with respect to x, y, and z. Overall scaling means whatever the factor I am using here, okay, at this particular stage, it is applicable to all the x, y, and z direction. So it is overall scaling. So for that purpose, I am using this one by one submatrix. Okay, so it is important for everyone to understand how this 4 by 4 transformation matrix, 3D transformation matrix, is partitioned and it is divided under different submatrix and what was the purpose of this submatrix. Okay, so this is what is represented over here. Okay, so with this background, let us understand, okay, let us understand the 3D translation, how 3D translation works. Okay, so I'm just moving to the point of discussion for the 3D translation. Everyone must remember this 4 by 4 transformation matrix and must remember that how these 4 parts, okay, 3 by 3, 1 by 3, 3 by 1, and 1 by 1 submatrix represented and what was the purpose. Okay, just now we have listed it over here, so it is very important to remember all these things. Okay, so let us start our discussion with the, I think we have cleared with the, okay, how the 3D point is represented in the, or a point is represented in 3D space, how I can represent in the form of the matrix, as well as we have seen the 4 by 4 general transformation matrix. I think this is also called as general transformation matrix. Okay, so let us continue our discussion and I'm just moving to the point of 3D translation. So start understanding the first basic operation which comes under the 3D transformation is 3D translation. Everyone knows that translation means, as we have learned in the 2 dimensions, so that I'm not explaining it more here. Translation means I'm going to shift or move the object. Now here the object is moved in 2D, it is moved only in the x and y direction. Okay, but here it is moved not only in x and y direction, but it is moved into the x, y, and z direction also. So we are going to move the object, we are going to translate the object, we are going to shift the object in the 3 dimension in the x, y, and z transformation. I directly come to the 3-dimensional translation matrix, how it is represented into the 3D translation matrix. Okay, so this is my 3D translation matrix, okay, which is used for the translation. You can find it here. All my diagonal values are 1. Diagonal terms is 1, here it is 1, here it is 1. So all these diagonal terms are 1, 1, 1. Okay, and just now we have seen that, which is the case we are going to produce the translation. So I require the parameter L, parameter M, and parameter N. So these L, M, and N are going to represent my translation factors. Getting me? So I think we have learned here, or we have already written it as, my translation factors are considered as the Tx. Okay, my translation factors are considered as Ty, okay, in y direction, and then I'm having this as a Tz. Okay, Tx, Ty, Tz. This Tx is nothing but my value L, okay, which is represented. My Ty is nothing but my value M, and my Tz is nothing but translation factor Z is represented with the value N. So L, M, and N represent translation factor Tx, Ty, and Tz respectively. Okay, so all of you understood how I am using my transformation matrix. Getting me? So let us continue our discussion with this. Now the translated homogeneous coordinate can be obtained using, okay, so how I will get it? Now this is my transformation matrix. Okay, just now I have seen this is my transformation matrix used for the translation, used for the 3D translation. Getting me? What is this? This is my original object. Okay, this is my original object, x, y, z, and 1. This is my values are, this is my transformation matrix, and this is my the expected output, or this is my transform point or transform object. Okay, so my transform object or the answer, okay, transform object or answer is equal to original object, that is this is represented by xyz1 multiplied with the transformation matrix having the value L, M, and N. Diagonal values are 1 and all remaining values are 0, 0, 0. All of diagonal values are 0 and only this lower row I am having the value L, M, and N represent my translation factors. Getting me? Now, this is what I'm having the 3D translation matrix. If I'm going to multiply this with this, if I'm going to expand it, okay, I'm going to expand it means I'm multiplying the original object this with the transformation matrix. Okay, then what value I will get for x dash, y dash, z dash. Okay, so this is my transform object. Okay, what value I will get? Yes, I will get this value. What is my x dash is equal to? Okay, what is my value of x dash? My x dash is equal to x plus L. Getting me? So I get the formula x dash is equal to x plus L. What is my value of the y dash? My dash value is y plus m. Okay, see, this is nothing but L is my tx, my m is ty, and my n is tz. Okay, so you can write it also here as tx, ty, and tz also. Okay, but generally we represent it as L, m, and n. Okay, we should represent. So y dash is equal to y plus m. What is the value of z dash now? What value I'm getting? Z dash is equal to z plus n. Getting me? I'm getting this value of z dash is equal to z plus n, and obviously h is equal to 1. Okay, so this is what I will directly get the formula for 3D translation. In 3D translation, I will get x dash equal to x plus L, y dash is equal to y plus m, and z dash equal to z plus n. So I'm just adding this translation factor tx, ty, and tz to get the appropriate answer. Okay, so I hope all of you understood easily three-dimensional transformation matrix. Okay, there is no need to understand what is translation, okay, or what is rotation, or what is scaling. Why it is so? Because we have already learned the basics of this type of transformation in 2D. Okay, so in the 3D we directly go to representation of the transformation matrix and how I will get this x dash, y dash, and z dash value, and so on. Okay, so let us continue our discussion. I'm just moving to the next slide now. Okay, now we are just considering an example here, because unless and until I show you the example, the point will not be clear how the 3D object is translated. Okay, now for that particular example, I'm considering a unit cube. Okay, so what I'm considering my object is a unit cube with one corner of the object is placed at the origin. Okay, so one point is placed at the origin. Okay, my unit cube is placed, one point is placed at the origin, and I just represent my 3D object as a unit cube. Okay, so let us understand how it is represented. So this is I have shown with the help of the diagram. I want everyone to look at how this unit cube is represented, because we have to draw the 3 dimension. Okay, not only the 2D. I want to show the object in the 3D. Okay, so I have shown this with the help of this. Now we can find here. Okay, so this is my x direction, this is my y direction, this is my z direction. Okay, I'm having this 3 direction x, y, and z. Okay, now my points are of this unit cube. My unit cube is represented with the points A, then it is B. Okay, we can find it, the point is C is here, C, then this is D, this is E. Then we can find that the point E has overlapped on the origin or at the center. So that's why the values of E I'm having are 0, 0, 0. Okay, so E's value, X value is 0, Y value is 0, and Z value is also 0, because the E point of this unit cube overlapped on the origin. Okay, so then I'm having E, then I'm having the point F, then I'm having the point G and H. Okay, so my unit cube is represented with how many vertices? I'm having 1, 2, 3, 4, 5, 6, 7, 8. So 8 vertices are there. Okay, or 8 vertex or 8 points are there of this unit cube, so that I have represented this particular object. Getting me? So this is my original object or 3-dimensional object which I want to translate. Getting me? Before that, now for translation I must multiply the matrix of this particular unit cube. Okay, so let us understand what is the matrix of this unit cube. In order to represent the object in matrix form, okay, in order to represent this object into the matrix form, we write all the points row wise one after another. Okay, we are going to write all the points row wise one after another, means A, B, C, D, E, F, G, and so on. So just look at how it is represented. Okay, so this is my object which is unit cube, I'm having the point here A, then B, then C, then D, E, F, G, and H. Okay, we have seen that E point is having the value 0, 0, 0. Yes, you can find that E is having the value 0, 0, 0. Okay, what is the value of A now? Let us understand how it is represented. A is having the value 0, 0, 1. In this case, which one is your X value? Yes, this is my X value. Okay, I'm just showing it here. This is my Y value and this is my Z value. Okay, this is X, Y, Z. So for A, if I look at this point, it is having the X value 0. Yes, it is correct. X is 0. What is the Y value? Y is also 0 because this is my X and Y. But I'm having the Z value. You can find the Z displacement here is 1. So I'm having A is having the Z value is equal to 1. Okay, and X and Y value is equal to 0, 0, 0. Getting me? Similarly, you just take or just cross check for any point that we are having. Okay, suppose I take this point as G. Okay, suppose I'm taking this point as G. So what is the G is having the value? X value is 1. Yes, it is correct. For this point, what is the displacement is X is 1. Y value is also 1. Yes, Y value is 1. So that's why this is X1, Y1, the point comes here. Okay, but what is the Z value? Z value is 0. So it is at the back side. Okay, it is not represented. Similarly, if I go for this particular point as a C, okay, if I go for this C point, you can find it is having the X1, Y1 and Z. Also it is 1. Okay, so it is having the Z value also 1. So C point is having the value 1, 1 and 1. Okay, so the same transformation, same object, original object I have represented. My original object is unit cube as shown in this diagram. Okay, I just add, if I want to represent it into the 4 by 4, then only this is added and this is nothing but my H value, and having this H value is equal to 1, 1, 1. Okay, so all remaining values A, B, C, D, E, F, G, H are same, and I'm just added, or I'm just going to add this 1, 1, 1 as a H factor, which is added for the homogeneous coordinate system, because my original 3D transformation matrix was 4 by 4. Okay, so I cannot have 4 by 4 multiplied by this. Okay, multiplied this 3 by or 1 by 3. I cannot multiply, or see, this is actually 3 by 1. I cannot multiply, so I convert it into the number of values to be 4. Okay, so that's why we are going for the adding this homogeneous coordinate with the value 1, 1, 1, 1. Okay, I hope all of you easily understood how my 3D object as an example. Okay, as an example, this is my 3D object called as a unit cube is represented here. Okay, is represented into the 3D values. Okay, it is having all this A, B, C, D, E, F, G, H point. It is stored into the matrix, and I convert this object into the matrix, and this is my 3D object called as a unit cube. Okay, in that case, you can find it here. This is shows the more interesting part, which represent or which is more similar to the object of the 3D, okay, which we have represented. Okay, this is my Z value 1. Okay, this is my X value 1, and this is my Y value, which is represented as 1. Okay, so after understanding the how the object is represented into the 3D, and now I want to go for translation of this object. Okay, I can translate this object in X direction. Yes, I want to move, so shift this object into the X direction. Also, I can move it into the Y direction, means I want to move this object to the right side. I want to move it to the upside. Okay, upside means this is Y side. Okay, or I can move the object into the Z side, means I want to move it to the front side. Okay, because this is my depth. Okay, Z indicate the depth, so I want to move the object maybe into the front side, more front side, maybe into the right side, maybe into the upside. Okay, right or left side, that usually represent it as X. I may want to move this object. I think I'm explaining you how the object is translated, so just understand. I may move this object into the right or left direction, maybe in this direction or maybe in this direction. Okay, here or here. Okay, indicate that I want to move the object in X direction. I want to move the direction, I want to move into the up direction or maybe to the down direction. Getting me? I want to move this object into the upside or downside, means in the Y direction I want to move. Whereas I want to move this object into the z or the depth direction, means I want to move this object to the front side, or I may move it into the back side. Okay, this particular object, and that is what operation we want to perform with the help of the 3D translation. Okay, so let us, I'm having one more slide, okay, where we understand if this object is moved, because if I move into all the direction, I think it will be more difficult for me also to draw or for you to understand. Let us have an example where I just want to move this only in one direction, okay, and how the object will look like. Okay, so that object I'm drawing with my, okay, color, okay, with my pen. So let us understand this. Okay, so I'm just moving to the next slide now to continue our discussion of the 3D translation. Now what type of translation I want to perform now? If I want to translate the unit cube only in x direction, okay, I don't want to translate into the y direction as well as z direction. I just want to translate only in one direction, so it will be easy for you also to understand, and it is easy for me also to draw the object. Getting me? So I just want to move or translate the unit cube only in x direction by, what is my translating factor? It is 2. My translation factor is 2. Okay, so that is indicate, if translation factor is 2, what it indicate? What is my L value? L represent tx and its value is equal to 2. L. So this is my L value. Okay, and L is nothing but is my translation factor as tx, whose value I want to set to 2 because I want to move into the 2 value. What is my M value? M represent ty. M is equal to ty, which is equal to 0, because I don't want to move into a y direction as well as I don't want to move into the z direction. It is represented by L, M and N. N represent it is z direction, which is nothing but my translation factor tz, whose value is equal to 0. Means I don't want to move in y and z direction. I just want to move the object only in the x direction by a factor 2. Okay, so now we are just going to look at how this object will look like, how it will be displayed. Okay, so I'm just showing the same, I'm just taking the same diagram as we have discussed now. Okay, so this is my original object now. Okay, so this is my original object, which is drawn with the black color. I consider that these are the black lines through which the object is drawn. Okay, now I want to translate this object only in x direction. Okay, this is my x direction, and with the factor, translation factor value is equal to 2. Okay, now what it will happen, what is going to happen in this particular case? Okay, so how my object will be displayed, okay, that I want to draw. Now suppose I am taking the scale here, so this is my 0, this is my x value 0, this is my x value 1, correct? And somewhere I want to mark, suppose this is my, I'm just extending this line, this is my, I consider x value is equal to 2, and I just extend this line. Okay, I'm just extending this, this is my x value 1 0, x value 1, consider this is my x value 2 here. Getting me? Okay, x value not z, it is 2, x value is 2, and I extend this line over here and consider this is my x value 3. Okay, so this is, I'm just extending the scale here, so this is 0, this is 1, this is 2, this may be 3 somewhere here. Okay, now what will happen in this case? Suppose I take the example of this point E. Okay, so E point is having the x value 0, y value 0, z value 0. Consider this E value. So x will be added with plus 2. Okay, because I want to translate into the x direction by 2, so this is my plus 2 value. Getting me? So the new value of E will be, x value is 2, y value 0 plus 0 means it will be 0, z value is also 0. Okay, so I'm getting this 2 value here. So I want to move this E point by 2 value. This is 0, 1, 2. So where this E point comes, the E points come over here. Okay, where this F point will come, F is having the value 1, 0, 0. 1 plus 2 means it is 3, x value will be 3, y value 0 and 0. So x value 3 means it is represented somewhere here. Okay, so I'm just drawing the diagram with my pen. So I want everyone will be in a position easy for everyone to understand it. Similarly, this H point, okay, if I consider it is 0, 1, 0. Okay, so this is the H point I'm having. It is represented with 0 plus 2 means it is 2. This is 1 and this is 2. Okay, x value, and y value is 1. Y value means that's why I'm having this is x0, y1. So this point will come somewhere here. Getting me? G point which will come somewhere here. Getting me? So I get this. I'm just connecting this. Okay. My diagram or drawing may not be that much perfect, but I think everyone will understand how the object, after translating it into the x direction by 2, how it will look like. Okay, now I have to also consider this point. Okay, a is shifted over here. You can find it, a is parallel line to this a. Okay, it will be shifted over here. 2 will be shifted at this particular stage. So I consider somewhere, okay, parallel to z axis. This is z. I need to draw some line which is parallel to this. Okay, suppose I consider it will be going to extend here. Also I need to draw the parallel line which is parallel to z. Getting me? And what is my scale for the z here? It will be somewhere here as z1. This also somewhere here as z1. Getting me? Similarly, these points are also extended from this as well as this. Okay, and I'm going to connect these points. Okay, so somewhere I'm going to connect these points. So I just get this, and this is also connected. Okay, this is the z value having the depth 1. This and this is also connected. This and this is also connected. Okay, so this is what I considered, not exact with the, I'm not having the exact scale to draw it, but I just want to show that this particular object, okay, so this diagram shows that how the object will look like after, see this unit cube, I'm just moving only into the x direction by the factor 2. So how this will be look like. Okay, so this will be just extension. This is my actual object that I'm having. Okay, so this is my original object, and this was my object which is, I call it as the transform object. Okay, so every point, every value which is having x, y, z value, x value is added by the factor 2 because I just want to move it into the x direction. Plus 2 means that's why I'm moving into the right direction. If I want to move in minus x direction, minus 2, I think the object will move in this direction somewhere here. Okay, so this is what my original object. Okay, so after transformation I just change the color so that it will be more easy for everyone to understand. I will try maximum, okay, the way the object will be transformed. So transform, this is my transform object. I'm just showing this each and every point over here. Okay, so just one more for the simplicity, I just considered, suppose I take the, my value is c, my original point is my original object is having the c point 1 1 1. Okay, so this is, which is my c dash now. So this is my, this is the point, I call it as my c dash. Getting me? So this is my c dash value, and which are the values or the point is having, see this is x is 1 1 plus 2. Okay, so I get this x value of the c point is 3. Okay, y value I'm not adding anything, so it will be 0. 0 will be added, so it will be 1, and in z also only 0 is added, so it is 1. So my original point is c, in original object is 1 1 1, but after transformation, I call it as transformation, I'm using 3D translation. So after moving or shifting this object in s direction by 2, my c dash value, okay, this point is now 3 1 1. And similarly I think it has reflected to the all the points, and this was my original object, and after transformation, I'm just showing it here, after transformation my object will be look like this. Okay, now if you are going to, okay, what I'm saying, if you are going to move this object into the y direction, what will happen, the object will be moved into this direction, it will be uplifted, or it may go into the downside. Or if I'm just moving this object into the z direction, this object may come to the front side. Okay, so similarly it is, all these things are applicable, okay, under my 3D translation. Okay, so it is very simple point for our for all of us to understand, and we have seen all the details of this 3D translation. It's how the point is represented in 3D transformation, how the object is represented into 3 dimension, what was my 3D translation matrix. Okay, so what is my tx, ty and tz value. Okay, and then at the end we have seen with the example how the object will look like if I am going to move the object in one direction, I have taken as a simple example only next direction, but you can move this object into the y direction as well as z direction, and accordingly you can draw the object or we'll get the object. What we need to do, if I am not, I think we are just showing it over here, but what we need to do is we just add to perform the matrix multiplication of the original object with the 3D translation matrix with the respective values of the tx, ty and tz. Okay, so as per the user requirement, and we will get the transform object which is similar to this. Okay, I hope all of you have enjoyed learning the 3D translation. Okay, so we are going to end our session here. Okay, thank you all the students.